Okay, so we'll take a look at the second half of section 6.2 and the section 6.5 part 2. And then the first thing they have us look at here is how to solve a triangle. Does anybody know what that means? Like, what do you have to find when you solve a triangle?
Is it all the angles and sides?
All the angles, all the sides. So there's 6 things to find. Some of those have to be given to you. Okay, so in order to solve a triangle, you have to be given a couple pieces of information. Okay. First thing is we're always going to be solving a right triangle. So that's a piece of information you already have. Every single problem we do has a 90. But in addition to that, I have to tell you 2 more things. And there's a couple ways I could tell you the 2 other things. One way is I could give you another angle and a side. So now you'd have a right angle, an acute angle, and a side. Or the second way, in addition to the right angle, is I give you the other 2 sides. Now, I didn't write up here giving you both angles. How come that wouldn't help? If you knew the right angle and then I told you the other 2 angles, that's not helpful. Yeah?
Because now you have no way to find the lengths of the sides.
Yeah, all you would know is that's like saying all the angles are 60. 60, 60, 60. How big is each side? Well, you couldn't figure that question out because it's an equilateral triangle and it could be any size. So no matter what information you have, you always have to have a side to get the scale. Okay? Either 2 sides or at a minimum 1 side. So we'll be using the Pythagorean Theorem and the fact that all the angles in a triangle have to add up to 180. Okay, so those are 2 important things. The other thing we're going to use is sine, cosine, and tangent. We're going to stay away from secant, cosecant, and cotangent. The main reason is the calculator doesn't have a button for it, so it's easier to stick with the ones that there's buttons for. Okay, and just as a reminder, what those functions are, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and then tangent is opposite over adjacent. So how would you know which trig function to use in the problem? Well, the way you figure it out is from the perspective of the angle you're trying to find. You're going to know one of the sides, and then the other side you're not going to know. Okay? So you have to figure out the names of those 2 sides. You have to figure out the name of the side that they're giving to you. Is it opposite, adjacent, or hypotenuse? And then figure out the name of the side you want to know. Is that opposite, adjacent, or hypotenuse? Once you figure out those 2 names, there's only going to be 1 trig function that would work. So let's say they give you the opposite and you want the hypotenuse. Well, opposite and hypotenuse would be sine. If they give you the opposite and you're trying to find the adjacent, then you use tangent. That's opposite and adjacent. And again, the choices are always either going to be sine, cosine, or tangent. We're not using the other 3 today. Okay, so when they give you a problem, a couple ways they can give it to you. They can just write out the information, kind of like a paragraph, or they can draw a picture and have you solve it. Okay. The first one I've done, I've just written all the information out. So it says one angle of a right triangle is 37 degrees, and the hypotenuse is 8. This is the first case where you're giving a side and an angle. All right, so let's make a sketch of that, because the sketch is going to help us to see what's opposite and what's adjacent. If you can visualize everything in your head, that's fine. If you can't, then draw it out. Okay. Doesn't matter how you draw your right triangle, that's just how I normally draw it, but you can have it facing any way you want. Just draw a right triangle. It says the hypotenuse has a length of 8. And it says one of the acute angles is 37 degrees. Does it tell me where to put it? No, it doesn't matter. Okay. If you're going to get all the same answers in the end. Okay. So I'm going to put it right there. And now I'm going to label my sides. Okay. We always use English letters for the sides. And there's one angle that I need to give a name to. From yesterday, what do we name the angle that's across from A? Yep?
Alpha.
Alpha. So the goal in this problem is to find 3 things: A, B, and alpha. Any question on the diagram? Okay, so what I'm going to do to kind of organize the information that I already know and what I need to find, I'm just going to make a table. Just put all my answers in one spot. Now, for now, we don't have to give a name to the angle across from C because it's always going to be 90. Eventually, we're going to use a third Greek letter when we don't have right triangles anymore. But for now, you can just write 90. Okay, so I need A, B, C, I already know, alpha, I can figure it out pretty quickly, but I don't know it yet. And beta is the angle across from B. It's 37. Right, so what could I find there pretty quickly without really doing, it's more just geometry. It's not even really trig at this point. Yeah.
Alpha.
Yeah, we can find alpha. How would you get alpha?
Subtract 37
Subtract 37 from
from 90.
90, and what would that give me for alpha? $53. Okay. So we've figured out one out of the 3 things. We've got the angle. Any questions on that? Now, to find A and B, I can use either angle. I can look at this problem from the perspective of alpha, or I can look at it from the perspective of beta. Which angle do you think is better to use for our perspective in this problem? Alpha or beta? Trigger? Which one is better?
Alpha?
How come?
I don't know.
All right, Leo, what do you think?
Well, it doesn't really matter, does it?
Technically it doesn't, but there is one there that I would definitely choose because of something. I have a very good reason why I would pick one of those over the other. Dylan, any thoughts on?
I'm not sure.
So there's a reason why I would want to use one of those angles over the other one, because I can't really give you a hint without telling you why I would choose it. What do you want to be like when we solve for A and B? You want to be careful that you're using information you know is right. Yeah?
You should use beta because they gave you the answer.
We should use beta because we know that that is correct. Okay? If you use alpha and you made a mistake finding it, like you subtracted or you hit the wrong button, well, if alpha is wrong, then you're going to get everything else wrong. So we're always going to use what was given to find other things. That way mistakes don't propagate through the whole problem. Okay, so now we have a choice. We can find A or we can find B. Let's do A first. At this point, you could do either one. It doesn't matter. Okay, so I want to know A, and I already know C, the hypotenuse. So now I have to figure out the name of the side, and I just told you one of them. The name of the side that I know, and the name of the side that I don't know, from the perspective of 37 degrees. So Shauna, what's the name of this side we've called A? From the perspective of the 37. Do you remember the two terms we use that are relative terms? Some reminder, just tell me the two terms, yep?
It's adjacent and opposite.
Adjacent and opposite are the two. So we just have to figure out which one this one is. It's adjacent, yep. So we want to know the adjacent. And Dylan, we already know the hypotenuse. So which trig function has adjacent and hypotenuse in it? Sine, cosine, or tangent? Yeah.
Cosine.
Cosine. So we set up our equation. It's the cosine of our angle that we're using. So cosine of 37 equals adjacent over hypotenuse. Okay, adjacent is A. Hypotenuse is 8. Now we got to solve for A. Okay, just get A by itself. Gracie, how would I get A by itself there? Yep. Multiply both sides by 8. And there's your answer. On this kind of problem, we do type it in and usually round it to 2 or 3 decimal places. Okay, I'm in degrees, so that's the first thing I'm going to change. And we have 8 cosine 37. Okay, so we get a length of 6.389. Okay, so I've got A. So I have one thing left to find. I've got B. Can someone give me one way that I could get B now that I know the other two sides? Yeah?
You could use sine opposite or 37.
Okay, so that's actually the better way. I want to do it that way. I was trying to lead someone into saying something else by now that I know the other two sides, but that is the way you want to do it. But there's another way you could do it, but I'm going to have an issue with that. Yeah. Okay, so now that you know two sides, you could use the Pythagorean Theorem. But why do I have an issue with that? Why might not that be a good idea?
Because your calculations could be wrong for A.
Right. Same reason we didn't use alpha. If you use A to find B and A is wrong, then B is wrong. So the way I'm showing you to find everything, you could make a mistake on one part, but still get everything else right. Because we're finding everything separately. So let's find B exactly the way Rebecca just said. So she said to use sine, okay, because now we're dealing with this angle, this side, and that side. So focus on what's in red. B is opposite. 8 is still the hypotenuse. So sine of 37 equals opposite over hypotenuse. And it turns out the variable's in the top again. That doesn't always happen. If hypotenuse was a variable, it could be in the bottom. But we multiply both sides by 8. And then type it in and see what we get. Before we type it in, I can tell you a couple things about it. I guarantee you that it is it has to be less than 8, right? Because the hypotenuse is always the biggest side. In fact, it even has to be less than 6.3 because the biggest side is always across from the biggest angle, and the smallest side always goes with the smallest angle. So I know it's less than 6.3. But whenever you add two sides together, they have to be bigger than the third. So if B was 1 unit long, that'd be impossible. That's too short. 1.1 units, that's too short. It's got to be at least like 1.21, roughly, something like that. So units, okay. So it's somewhere between 1.21 units and 6.3 units. Does anybody have the answer what it comes out to? Gracie?
4.814.
4.814. Now what we could do, just to check our answer, not to find it, but just to check it, take 6.389, square it, take 4.814, square it, and I get 63.99, which is basically c squared. 8 squared would be 64. Right? So the Pythagorean theorem is a good way to double check. And because that worked, I'm pretty sure we got everything right. Questions on that? Anybody want to see another one of that type? That's the same type as the last one. They're giving you an angle, they're giving you a side. Okay. You could choose what you want to find first. I usually get the first angle, so beta would be 70, and then I go from there. But you can find anything you want in any order you want. Any questions on that? Okay. So let's look at the case where we have two sides. So this one says the hypotenuse and one leg of a right triangle measure 12.7 and 6.1. And respectively means the numbers that they give you are in the same order as the names of the sides. Hypotenuse, leg, hypotenuse, leg. Even if they didn't say respectively, if you're given two numbers, you know the bigger one has to be the hypotenuse. The smaller one could not be the hypotenuse. Okay, so let's make a sketch. It doesn't matter what side is A and what side is B. They're just the legs, so I usually put A and B on the bottom. C is the hypotenuse. And now I'm going to fill in what I know. It says, let's see, the hypotenuse is 12.7. So we'll call that C. And does it matter which side I make 6.1? I have a choice of A or B. No, it doesn't matter. So it's about Jay, and what side do you want to make 6.1? A. Okay. So A is 6.1. Dylan, the name of the angle across from A?
Alpha.
Alpha. And Tanya, the name of the angle across from B? Beta. Okay, so let's make a chart of everything we need to find. So we've got A. B I don't know, but C I know. Okay, alpha, we don't have that. And beta, we don't have that either. And of course we always have the angle across from C. For now it's a 90-degree angle. Okay. So what can we do in this problem that I'm okay with this time, but I wasn't okay with in the last problem? Yeah?
Use the Pythagorean theorem to find the other side length.
Okay, we can use the Pythagorean theorem because everything we're plugging into it is given. Okay? So it's okay to use that here. So let's set that up. Caleb, can you set it up for me with my numbers?
6.1 squared. plus b squared equals 12.7 squared.
All right, so we're going to get b equals, we're going to have to take 12.7 squared. We're going to subtract the 6.1 squared. And my last step to get rid of the exponent on b, Trevor? What's my last step? To get b?
Square root.
Yep, we'll take the square root. Hey, so I'm just going to type all that in at once, and by doing it this way, I'm not rounding anything off until the very last step. Rather than take 12.7, square it, and then round it, 6.1, square it, round it. There's no rounding until the very end here. Okay? And that's a better way to do it. So square root 12.7 squared minus 6.1 squared. Okay, so we get 11.139. Okay, now I can tell you alpha is going to be the smallest angle, and beta is going to be bigger. Just because it's not exact, but B is almost twice as big as A, it doesn't mean beta is going to be almost twice as big as alpha. That doesn't work. But beta is definitely bigger than alpha. Okay. All right. How about thoughts about using B now to solve for alpha and beta? Should we use B? Juliana, what do you think?
I don't think we should.
I'm just putting something on your chair.
It's not a thing that we got, like in the problem. It's something we solved for, so it's wrong.
Yeah, so let's skip using B because it could be wrong. I'm going to go back to using just A and C. So I'm going to circle two things, A and C. And let's pick an angle we want to find. Let's do alpha. Okay, so now we're finding alpha. So this was to find B, and this is going to be to find alpha. Okay, what trig function would I use to find alpha? Figure out, in this case, it's not the name of the side you know and the name of the side you want to know, it's the name of both sides you know. Okay? The variable is going to be in a different spot.
Sine.
Yeah, so we could use sine, opposite over hypotenuse. So the sine of my angle equals 6.1 over 12.7. Now, let's set it up to find beta too. Now, when you're finding a different angle, you're changing your perspective. Okay, so from the perspective of beta, what are the two sides that I know? Yeah?
Adjacent and hypotenuse.
Adjacent and hypotenuse. So that would be, yep,
Cosine.
cosine. So the cosine of beta equals 6.1 over 12.7. Now, what's different in both of those equations is look where the variable is. The variable is not part of the fraction like it was in this problem. Okay, the variable was the numerator in the fraction. In this problem, the variable is inside a function. It's kind of like if you had this. Square root of x equals 9. You can't do anything to that x. Let's make it 2x. You can't do anything to the 2x until you get rid of the function that's protecting it. Okay. Same thing here. You can't do anything to this alpha till you get rid of the function that's protecting it. So when we have a square root, we use a function that's the opposite. We don't add, subtract, multiply, or divide by square root. That won't get rid of it. Only way to get rid of square root is square. It's the inverse function. Well, trig functions also have an inverse. Okay. So what we have to do is cancel out cosine in, if we're solving for beta. We're going to do the same thing to cancel out sine when we solve for alpha too. But I'll start with the cosine. So to cancel out cosine, we have to use a function that's the inverse of cosine. And we just call it inverse cosine. It doesn't have a different name. Just inverse cosine. Okay, so there's a couple ways you can write inverse trig functions. You can write the trig function with a -1 in the spot where an exponent would be. I think what's a little confusing about the notation with a -1 is that if you had something like this, sine with a 2 up high, that does mean to do this. That does mean sine times sine. When you have a -1 up high, normally -1 means to flip. It doesn't here. So when you have a -1 as the exponent, it's like where the exponent would be, think of that -1, it's just a symbol that means inverse. If you have any other number in that spot, it is an exponent. If you have a -1 in that spot, it is not an exponent. Any question on that? Okay, another kind of way to say that is that this is the same as this. They mean the same thing. But this is definitely not the same as that. It's not the same thing. Okay. So any number there except the -1, you can think of it as an exponent. If it's a -1, just think in your head, okay, -1 is just a symbol that means inverse. That's all. Another way to write it to avoid that confusion is to write arc sine. Okay, that's another name for inverse sine. It means exactly the same thing. Arc cosine and arc tangent. There is inverse secant, inverse cosecant, and inverse cotangent. But for now, we're not going to use them for the same reason we're not using the other regular trig functions. There's no but. Okay? But we'll come back to them later. Okay. So when you do operations with these, you do not add, subtract, multiply, or divide. Okay? Just like if I had that. If I asked you how to solve that, you don't say add, subtract, multiply, or divide. That is not the right verb to use. In this case, you could say it two ways. You could say square both sides. That's the verb, you're squaring. Or take the square of both sides. That's how you solve it. You don't add the square root, you don't subtract square root. You can't do that. Okay, it's the same thing here. When we use these functions, we can take the inverse sine of both sides. Or we can take the inverse cosine of both sides. You don't multiply both sides by inverse sine. That doesn't make sense. Okay? Multiplication is something you do with numbers and letters, not words, not functions. Okay, so let's look at this one. So I've got sine of alpha equals 6.1 over 12.7. What's the function that cancels out sine? Yeah?
Arc sine.
Arc sine or inverse sine, yep. And Can you explain how I use that in this equation? I'm just looking for how you would phrase it.
Take cosine both sides.
Yes. Take the arc sine or take the inverse sine of both sides. So what you're really doing is you're plugging all of this stuff into the function inverse sine. Okay. And same thing on the right. You're plugging this fraction into the inverse sine function. Think of inverse sine like a box. You're taking that fraction, you're dropping it in the box, and it's going to give you some kind of answer. Okay. When you do it on the left, inverse sine and regular sine cancel out. When you do it on the right, take 6.1 over 12.7 and plug all of that into the inverse sine function. Okay, we get 28.706. Now, if I was running out of time and I had to get beta quickly, technically I could subtract it from 90, and it should come out to 61.294. But if I do it that way, what am I relying on? Yeah?
I got alpha correct.
Right, I'm assuming I got alpha correct. So let's find beta the way we have it set up. But we already know, and this is kind of helpful, we already know it should come out to 61.294. Okay, so keep that number in mind. Okay, so let's solve for beta. What am I going to, or what function do I use here to get beta by itself? Jason?
Arc cosine.
Yeah, so we can use arc cosine or inverse cosine, and I'm going to take, I'm just going to squeeze it in this time, the inverse cosine of what's on the left. I'm going to take the inverse cosine of what's on the right, and let's see what we get. So, inverse cosine of 6.1 over 12.7, I get exactly the same thing. So the fact that I got the same answer for beta two different ways confirms I probably did it correct. Okay. Any questions on that one? So there's a pattern to when you have to use inverse sine and when you don't. If you're solving a problem with two sides, you're going to have to use inverse trig. Inverse trig always is used to calculate an angle. The reason we don't use inverse trig with case 1 is because you know all the angles right away. You're given a 90, you're given an angle, just subtract that other angle from 90. You already know all your angles. Okay, so inverse trig is only used when you need to find an angle. That's it. Just like Pythagorean Theorem is only used when you want to find a side. You'd never use Pythagorean Theorem to find an angle. It doesn't work that way. Okay, anyone need to see another one of this type? Where you have a side and a side. Okay, so the three calculations you'd have to do here, Pythagorean Theorem, that would give you A, and then use inverse trig to get alpha, and then use inverse trig again to get beta. All right, so we've talked about unit circle. Before, and before I even get into that diagram, I just want to remind ourselves what the unit circle definitions were for sine, cosine, tangent, and all that. Does anyone remember from unit circle, and I might have reviewed it yesterday a little bit, what letter was sine equal to? Leo?
Y over R.
So on a unit circle, r would be how much?
1.
1. So what's y over 1?
Y.
Just y. Yep. How about cosine? Abby?
That was X.
That was x, and then the tangent is the quotient of sine and cosine. It's y over x. And now we could take all those and flip them. 1 over y, 1 over x, and x over y. So those are our definitions of sine, cosine, and tangent on a unit circle. Okay, we did those, I think, back in section 6.2. Well, now what we're going to do is we're going to extend those definitions a little bit so we don't just have to use them on a unit circle, but we could use them on any circle. And kind of the simple way to visualize it is, look at that side. In the small triangle, what is that side? It's the what of the triangle? Yeah? It's the hypotenuse. Well, now, instead of just looking at the small triangle, we're going to look at this bigger triangle. That bigger triangle has a hypotenuse. I just traced it in red. But the hypotenuse is no longer 1. What is the hypotenuse in that bigger triangle? Yep. Just let me make that clear. So we'll call this whole thing from there to there, we'll call that R. So how big is the hypotenuse in the bigger triangle? Yeah. Yeah, R. R covers that whole distance. Not just the distance on the outside of the small circle. So basically all we have to do to adapt the formulas for unit circle trig to make them work with a circle that's bigger radius, or a radius that's not 1, is everywhere we had a 1, which was the hypotenuse, change the 1 to an R. Because now the hypotenuse, or the radius, is bigger, or it could be smaller than 1. So what happens is, instead of y over 1, because 1 was the hypotenuse, now it's y over r. Instead of x over 1, now it's x over r. And instead of, well, actually for tangent, it stays the same. Let's see why it stays the same. Why didn't that one change? What was our old definition for tangent? The original one on the unit circle? Yep. It's y over x. On the new circle, y, well, actually I'll write it right here. Y turns into y over r. X turns into x over r. So there's my old definition for tangent, y over x. Here's my new definition, y over r divided by x over r. Well, when you have fractions that are in the top and the bottom, if they have the same denominator, it cancels out. Just like taking and multiplying by the reciprocal of the bottom. The r cancels out, and you're left with exactly what you started with. So that's why tangent doesn't change. And cotangent is just the reciprocal. Okay. So there's our 6 definitions. We kind of touched on them yesterday, but I didn't really explain in a lot of detail about like why tangent stayed the same and why we use an r instead of a 1. Okay. It's a different hypotenuse, that's all. All right, so let's see if we can find the 6 trig functions of an angle where 2, 3 is on the terminal side. So we're going to use the definitions we just had. That's x. That's y. What letter am I missing to be able to figure out the sine, the cosine, and everything else?
R.
I'm missing r. Oh. We don't really need graph paper, just sketch it roughly. So right 2, up 3. There's your r right there. Okay? It's the radius of a circle, but it's also the hypotenuse of that triangle. 2, 3. So how would we get r? Knowing the length of each leg. Well, see it?
Sorry.
How would we get r if we know each leg?
Which one's that?
Well, r is what we have to find. R would be the radius of this circle, if I were to draw it in. And I can't draw it. Sorry.
R is just the hypotenuse.
Yep. And how would you find that?
Good. Use tangent or Pythagorean theorem.
Yeah, we couldn't use tangent, but we could use the Pythagorean theorem, right? So it would just end up being the square root of, you know what? Let me put it over here. Square root of 11. Square root of 13. Okay, any questions on that? So now we've got x, we've got y, we've got r. Let's fill in our definitions. Jane, what would the sine of this angle be?
It would be 3 over square root of 13.
Yeah, so it would be 3 over square root of 13, and then we fix it. And that's really just doing opposite over hypotenuse. It's exactly the same thing. Think of it as y over r, think of it as opposite over hypotenuse, same thing. Megan, how about my cosine?
2 over square root of 13.
Yep, and once you fix that,
2 square root of 13 over 13.
over 13. And the tangent would be y over x, opposite over adjacent. Think of it either way, 3 over 2. Okay. The other ones, let's see, we're going to have the reciprocals. So cotangents, pretty quick, 2/3. My cosecant, what would that be? Yep.
Square root of 13 over 3.
Yep. Square root of 13 over 3. And the secant, square root of 13 over 2. Okay. So that's finding all 6 trig functions of an angle that's in quadrant 1. Let's solve for that angle. I want to know how big it is. Now, any one of those 6 equations is enough information. If I solve any of them, I get how big the angle is. Let's stick with one that's pretty easy to solve. Sine of theta equals 3 root 13 over 13. Okay, so how would I take that to the next step now and get theta by itself? What trig function would I have to use? Yeah, Rebecca?
We just have to use inverse sine.
Yeah, we're going to take the inverse sine of what's on the left. Take the inverse sine of what's on the right. Type that in, and that's how big that angle is. It's the inverse sine of 3 root 13 over 13. Now, you don't have to use inverse sine. You could have done the next equation down, which was inverse cosine, or the one below that, which was inverse tangent. There's a reason I picked this, and I'll tell you in a minute. So 3 root 13 divided by 13. So that angle is 56.31 degrees. makes sense because if you look at my sketch, it's an angle in quadrant 1 where we've gone up more than we've gone over. So it's more towards 90 than it is towards 0. Okay. If I made that y value even higher, then the angle would start to increase even more. Any questions on that? All right. So if we're in quadrant 2, 3, everything works fine because we're dealing with acute angles, angles between 0 and 90. The problem can come in if we're in a different quadrant. Okay. Before I show you what you need to do, let's just look at this problem. You don't have to copy it down yet. We're gonna come back to it, but I'm showing you what happens and why I'm gonna show you how to fix it. Let's graph the point 2, -3. So now, if we're labeling the side lengths in the triangle, that side is still 2, that side is still 3, and the hypotenuse is still square root of 11. It's the same triangle. So if you were to find theta, what you would be finding is this angle right there. But what they really want to know is this angle. The question is always, what is the angle from the positive x-axis met all the way to the hypotenuse? That's always the answer they want. And that's exactly what we gave them right here. What was the angle from the positive x-axis all the way to the hypotenuse? The difference was that the answer that they wanted was the angle that was inside the triangle. So we didn't have to do any extra work. The angle inside the triangle here is not the answer. Okay? It helps you to get the answer, but it's not what they're looking for. Can anybody tell me what the answer would be? Like, what would you have to do with that angle that's inside the triangle to get that angle in red? Yeah.
Would you just subtract that angle from 180?
If you subtracted from 180, it would be up here.
Or from 360?
From 360, yeah. So there's different formulas, and the one you just mentioned was subtract that angle from 360. That's exactly what you need to do in the fourth quadrant. Subtracting it from 180 is what you need to do in the second quadrant. All right, so if you're in quadrants 2, 3, or 4, what you want to do is find what's called the reference angle. The reference angle is the angle inside the triangle. Okay, come right back. I just want to show you something. So in this problem, that's the reference angle. If you had a triangle in quadrant 3, that's the reference angle. If you had a triangle in quadrant 4, that's your reference angle, or quadrant 2. The reference angle is always the angle that's near the origin. It's tucked between the x-axis and the hypotenuse. So, to find that angle, take the absolute value of the inverse sine. So even if the numbers are negative, we don't have to think about that. Just take the absolute value of whatever you get when you do inverse sine. That's your reference angle. From there, if your coordinate was in the second quadrant, subtract from 180. If it's in the third quadrant, add to 180. If it's in the fourth quadrant, subtract from 360. And even if you don't remember these formulas, even by me just putting up the example, Jane was able to figure out, looking at the picture, oh, just subtract from 360. You could kind of reason it out. But this just kind of helps us to do it in our head. Okay, so let's look at our problem. Right, so it says to find the inverse, the absolute value of the inverse sine. So I already know my angle is from that perspective. It's tucked right near the origin, and it's opposite, which is 3, over hypotenuse, which is square root of 13. So in this problem, whoops, I'm sorry, technically that's a negative. Okay. So inverse sine is y over r. Y is negative 3, x is 2, I don't need it here. R is the square root of 13. Now, if we do that out, we're going to get what we just got before, 56 point, whatever it came out to. Also, it doesn't matter if you type in a calculation with a square root in the bottom, that's okay, because that's not the final answer. So, negative 56.31, but remember, we're taking the absolute value to make it our reference angle. So what I'm finding is this, right there. So 56.31. We already had that. Now, quadrant 4, subtract it from 360, and that's the answer to the question. So 360 minus 56.31. So that angle in red, the big angle, is 303.69. Obviously, we're not really dealing with an angle in a triangle now because that angle is huge. It's way bigger than 180. So any questions on that? That idea is going to it's going to come up quite a bit when we start to solve inverse trig functions and we have to get multiple answers to a problem. The calculator will never give you the second answer, but if you can find one answer, which is like your reference angle, you're going to have a formula right here to get the second answer. All right, special angles that you kind of have to be careful with, you can't really use the formulas that I just showed you, is if it's 0, 90, 180, or 270. Those are quadrantal angles. When you have a quadrantal angle, you can't draw a triangle. Okay. Let's say you draw, let's say you had the coordinate, we'll say 0, 3. Well, the problem here is x is 0, right? Y is 3. And then what's the radius? Well, I guess if you want to think of, you could think of y and the radius really being the same thing. Right? You can't draw a triangle because to draw a triangle you have to draw a line from the origin down, but that's just a line segment. If the point was over here, then I could draw from down and over. But once it gets here, it's like the hypotenuse and the y become the same. All right? So those are kind of special cases where you can't draw a triangle. That's just what I'm trying to show you. And the answers always come out to 1, -1, and 0. When you're finding the sine, the cosine, the tangent of any of those numbers, you always get a 1, a -1, or 0. Okay, and the last thing I told you I'd show you is a chart that tells you where trig functions are positive and negative. Okay, so I've labeled a diagram. And in that diagram, it's separated into quadrants. The upper right quadrant has an A, and then going counterclockwise, it's ASTC. What that means is if you give me any angle in quadrant 1, okay, 76 degrees, if you take the sine, the cosine, or the tangent of 76 degrees, it will come out positive. All trig functions are positive in quadrant 1. In quadrant 2, now you're looking at angles that are between 90 and 180. The only trig function that results in a positive answer is sine. So Leo, can you give me a number between 90 and 180?
100.
100. If I take the sine of 100, I guarantee you it's positive. If I take the cosine of 100, I guarantee it's negative. And the tangent of 100 is also negative. If you give me an angle in the third quadrant, the tangent is the only calculation that will come out positive. And the cotangent, because tangent and cotangent are just reciprocals. So obviously, if a number is positive, then so is its reciprocal. In the fourth quadrant, the only trig function that comes out positive is cosine. Right. So can somebody tell me where would tangent come out negative? Which quadrants? Rebecca?
Quadrant 2 and 4.
Quadrants 2 and 4. Yep, tangent would be negative. Where would cosine come out positive? What quadrants does cosine have positive answers? Leo? 1 and 4. Yep. That's how you use that diagram. Okay. Not super important right now, but it's going to become very important with stuff we do later on. So keep that diagram. That diagram and the 4 formulas we had right here, keep those in a good spot to look back on. Okay, so homework tonight, this is the last homework assignment that's going to count on term 2. It's page 361. 25 to 34, 40 to 42, 45, and then on 49 to 53, just the odds, and then 57, 61. Okay, we'll go over that tomorrow, and then that'll finish up chapter 6. And then we'll take a quick look at the first part of section 7.2, which is more on inverse trig functions.